the phase by 90 degrees overall. Here the phase will be negative 45 degrees. Here the phase will be 0. Because remember, if the body diagram is flat, in the flat region you can only have either 0 or 180 degrees phase, nothing else. And when the phase, when the slope is positive or negative, 20 degrees per decade, going down, going up, the phase over here can only be either plus 90 or negative 90, positive 90, negative 90 degrees per degrees. Here, another pole, phase is
minus 90 by
negative 45 degrees, because it's just the frequency of 0. Here, after far after the pole, we have negative 90 degrees. How much is the phase margin? 90 degrees. Stable or unstable? Stable. Good. Now, let's suppose that this 0 is a right F-plane 0. Right F-plane zeros have the same magnitude effect as a left F-plane 0, but phase for RHP is like a pole in the left HP. So, phase is negative 45, negative 90,
negative 155.
Negative 180. Our phase margin has gone, well, not yet sure, but if I want to decrease, to go down from here to crossover, I need to add a pole. If I add a pole, here I will have a negative 225 degrees, here negative 270 degrees. How much is the phase margin? Lost a long time ago. And there is no way to compensate for it. Don't come out with the bad idea, very bad idea, to put here a right F-plane pole to cancel the right F-plane 0. Cancellation doesn't work in this world. Because if it is not exactly on top, it will diverge anyway. Even if you have a 0 and you want to compensate with a left F-plane 0 and you want to other way around, sorry. You have a left F-plane pole and you want to compensate it with a left F-plane 0 on top of it, it works only for non-precision systems. A scope is like this. When you turn with the screwdriver the probe compensation screw, you are moving a pole, a 0 on top of a pole on top of a 0, so you compensate for the. But this is not a high precision system. A high precision system, just forget cancellation. If you don't like a pole, move it, don't cancel it. So, if we have a right F-plane 0, the only way to get stable is to cross over before the right F-plane. No, nothing else that you can do. Okay? And so, my right F-plane 0 has this frequency. We have to look for the minimum of this frequency and we have to cross over before this frequency because the right F-plane 0 cannot be compensated. And this happens also for a boost converter, for a buck boost converter, for a choke converter. In a choke converter you can change the schematic and remove this right F-plane 0, but if it is there, you cannot compensate. I told you that the boost converter is used for PFC. And it can be used for PFC because in a PFC, my bandwidth, the crossover of my control system, has to be less than, quite lower than the phase, the line frequency. So line frequency, rectified line frequency is 100 Hz. My crossover frequency maximum can be 10 Hz. This 0 is higher than 10 Hz, and so I can use a boost converter in CCM for a PFC because I have to cross over at 10 Hz next. But in any other cases, be careful because you have to cross over far below this right F-plane 0 frequency. Okay? So far so good? Now, let's consider another transfer function. Still key. We will see that our transfer function, our loop gains won't be like this, but two complex conjugate poles, so my slope comes down with negative 40 dBs per decade. Here we have a left at plane 0, a little bit higher. Let's say here we have left at plane 0, and here probably we can have another pole. Stable or unstable?
Probably unstable because we cross over with the minus 40 degrees.
Okay, if you learn that if you cross over your you cross over with a slope of negative 40 degrees per decade, it's unstable, and if you cross over with negative 20 degrees per decade, it is stable, just okay, it's wrong.
Maybe.
Maybe. So if a criteria tells you a maybe, it's useless. If you cross with 40 degrees per decade is unstable, quite sure. If you cross over with negative 20 degrees per decade, could be unstable if you have a right at plane 0. Gain margin, crossover slope, just forget that. The only good ways are Nyquist or phase margin. Let's look at the phase margin of this system. Here phase is 0. I put it. Here you are descending 20 degrees per, 40 degrees per decade, the phase is
Negative
180 degrees. Here I placed this 0 just at the crossover. How much is the phase margin?
Negative 135.
Here the phase is negative 135 degrees. That means the phase margin is 45 degrees. And here we have another pole, it's after the crossover. If it is far enough, does not make any noise, any mishap. But if this pole that is beyond the crossover frequency is not too far, let's say it's just a factor of 2 above the crossover frequency, what we get is that this pole just decreases my phase margin. But probably it's still stable. Okay? Stable or unstable? Reasonably stable, probably. Now, let's suppose that my 0 moves. Oh, it's not a right at plane 0. This is not a boost converter. This is just another converter. Let's suppose that this 0 moves over here for any reason. So, we have something like this. We cross at 40 degrees per decade, we have a 0 cancelled by a pole, or almost cancelled by a pole, and then we keep going down. Stable or unstable?
Probably unstable.
That is unstable, basically. If the 0 moves after the pole, this is definitely unstable. Why? Because we lost the good service of the 0 that is boosting the phases, making my system more stable. When you add a 0 to your system, you increase the phases, so the phase margin improves. Oh, look, there is a left at plane 0 that moves higher and system becomes unstable. What is a left at plane 0 coming from in power electronics, at least up to today? Yes, sir. That means if you get a lousy capacitor, output capacitor, your system can be stable because the low frequency 0 due to the ESR stabilizes your system. But if you change just the manufacturer of your capacitor, instead of let's say 220 microfarads, you get another 220 microfarads, better quality. Your left at plane 0 due to the ESR goes up in frequency, goes up by a factor of 3, 5. Your left at plane 0, this 0 over here, that was stabilizing your system, moves above, past the crossover frequency, and your system becomes unstable. That is what happened to the company I told you about when I presented this problem. They didn't change any value. They changed just the manufacturer of the capacitor. The capacitor was still same voltage, same working voltage, same output, same capacitance, and all of them, all the power supplies become unstable. Why? Because they were better capacitors, technology improved. Better capacitor means higher zero, means lower, smaller ESR. Higher zero went above the crossover frequency, was not stabilizing anymore, the system became unstable. Ouch. Okay? So far, what besides finding the transfer function, the important point is that the output capacitor 0 is important. You have to consider it while designing the control system. Okay, so far so good. Are you still with me?
Professor, sorry. If ESR decrease, the 0 moves to
higher frequency.
To the right.
Yes, because the F0 is equal to 1 over 2 pi C times ESR. So if the ESR decreases because you get a better capacitor, the zero frequency goes up. You need to know that it is, more or less. At that time, remember, there was not any theory. They didn't know this. There were gurus trying to find out if it was working or not, and the casuals, they randomly placed this 0 before just before the crossover frequency, or at the crossover frequency, and when it moved at higher frequency, stabilization was not there, stability was not there anymore. Okay, so far so good?
So a better capacitor gives me better performance.
Better capacitor gives you better performance, it's less ripple and things like this, but you have to know where the 0 is. It's not better capacitor that makes my system unstable. Makes your system unstable because you didn't design it to try that till it works with that capacitor. If you can design it, this doesn't happen. Okay, on Friday we will start with the switch averages, because this system to solve the circuit worked. We found a solution. You can apply to any converter, and I had once a student making his thesis with me, and we had to analyze a different topology that was not found in literature to was the transfer function. He applied this method and he got the result, no problem. But it's a heavy method. It's very complicated. Why? Because we are averaging all the circuit completely. Even if in your circuit you have an inductor, you don't need to average an inductor. An inductor is an inductor. You need to average a switch. That is the troublemaker, but not inductor or a capacitor. Capacitor is a capacitor. It's not changing in time. What changes in time are switches. So next time, instead of solving all these differential equations, we will solve only the equation for switches. That would be a smarter way. It's like, this method is like if when you have an electronic circuit with transistors working linearity, instead of finding the bias point and changing, substituting each transistor with its model, its linear model, you write down the differential nonlinear equation for all your circuit and you try to solve it. That's okay, but it's not a smart way. Smarter way is just find a bias point and for each nonlinear component substitute its linear model. Not solve the nonlinear equation for all your circuits. That is a lot of pain in the neck. That is exactly what we did in this moment. But this was the first result they got. And it's still a very systematic way to solve it. In some cases, it's the only way you have. I want to have some fun now. Let's consider a system that is something like S minus 1, the transfer function as 1 over 1 plus S. And the system with this transfer function has, let's suppose, a step applied to it. This is the input to this transfer function. And what is the output from a transfer function like this? Okay, everybody knows.
Transfer function times 1 over s. Oh no, it's a step.
No, step.
I get my gum, put some salt in it because I am nice, so I just fill it with salt. What is the output?
1 minus e raised to e minus.
Okay, that's what I like it. Please don't tell me the step function, I don't know how you call it. No, this is step function. HT, no, it has a name. Yes, but it has a symbol, heaviside function. UT. It's not UT times 1 over 1 plus s. If you do something like this, you can be very angry. Okay. In time domain is something like this. Okay? Let's put here 0.5 s plus 1 over s plus 1. We have a pole and a zero. What is the time domain solution for this transfer function? Without taking the inverse plus form of that stuff multiplied by 1 over s. Initial theorem value, final theorem value, something like this. That's very easy. Oh, please, I should stop the recording because I am telling you something that I don't want that goes out from this class. Don't publish it on YouTube. A step, you can imagine it, is not wrong. It's just said in a very hands-on way, a very manual way. This step, this vertical part has infinite frequency, this horizontal part has 0 frequency. So, when you take this step, you look, what all the capacitors are short circuits, all the inductors are open circuit, or in this transfer function, as goes to infinity, it means that the gain is 1/2. So, your step will be moved to the output with 1/2 of the height, and then it will go exponentially to the final value. If your transfer function is 2s plus 1 over s plus 1, with the same input signal, you will get something that goes up above the final value, because the limit for s going to infinity is 2, so the step, which is infinite frequency, has a gain of 2, and then it comes down to the final value. You know it. One pole and 0 undercompensated, pole and 0 overcompensated. That's standard stuff. Transfer function 1 minus s divided by 1 plus s. Here we have a right half plane 0. You see this negative sign. What's the output? Negative? Strange. Why? Well, because if you take the this is infinite frequency. For infinite frequency, what is the gain of this transfer function? Negative 1. So your output will go negative 1, and then we go to the final with the same time constant. We go to the final value. This is the bad effect of your right of plane 0. It starts from the wrong direction and it says, oh, sorry, it was the other way around. Let's imagine that your car has a right of plane 0 between the steering wheel and the wheels and the direction where you go. That means that if you see an obstacle and you turn the steering wheel to the left abruptly, your car goes to the right. And then after a while tells you, oh, sorry, you wanted to go to the left, and it starts to go to the left. Let's suppose that you are driving this car and you are drifting a little to the right because of any reason. So you turn your steering wheel to the left and your car goes more to the right. And you start to panic and you steer more to the left and your car goes more to the right until it gets a tree or there is on the right hand side. Is it an easy car to drive? No. Fortunately, cars are not like this. What is the only way to drive a car like this? If you want to go to the left, you don't go abruptly to the left. You move slowly to the left. If you move it slowly, it means that you don't have a mass turn, you don't have high frequency because you are going slowly, and so you get your DC gain. That means crossing over before the right plane zero. You are lucky that cars are not like this, but airplanes are. In an airplane, you move the yoke to the left, the airplane banks to the left and goes to the right. That is not nice. Fortunately, an airplane is not single input, single output system. Two inputs. There is yoke and there are pedals. So you go to the left with the yoke, the airplane banks to the left, you apply left rudder and the airplane turns in the right direction. This happens for airplanes having very long wings, like gliders, or with swept wings, like liners. In a liner, fortunately, there is a servo system that applies automatically rudder when the captain moves the yoke. But if this system that is called yaw damper, because it also damps some parasitic oscillations that are in the airplane, if this yaw damper fails, it's very hard to keep the airplane flying. And when I say very hard, it means very hard, because it becomes unstable. Anything you do, either you do it very slowly, or you excite the instability. It goes in the other direction. And if you go very slowly, and you have to correct because you are not aligned with the runway, either you go fast, you align, but you become unstable, or you land outside the runway. It happened. It happened that an airplane was flying without the yaw damper, and it became badly unstable, and the captain was able to return to fly back and land. There were no passengers on this plane, there was just a test flight, but it was really hard. There is on YouTube, the video is really impressive. Supersonic fighters. Supersonic fighters, when you pull the yoke, it's not a yoke, it's a stick in a fighter. You pull the stick to go up, the fighter goes down and then climbs. And this effect, the zero right after zero, was found by an engineer who solved the system and said, okay, if you want to gain altitude in a supersonic fighter, instead of pulling the stick, just push it abruptly and pull slowly. And so push it abruptly means you go up due to the right of plane zero, and then you pull and you keep going up slowly. And this engineer told the pilot this story, and the pilot said, come on, it's not true. If my target is over there, I pull and go over there. And he tried to get somebody trying it, and obviously the pilot didn't want to try it, because I know how to fly a plane. If my target is over there, I pull and get it out. Okay. Fortunately, the commander of the base of this military base tried to say, okay, we can make a try, and order to his pilot to try it. And the discovery was true. That means if you want to go up fast, you have to push abruptly and pulling up slowly. And so they were able to climb faster to get to the target. So the right of plane zero is really very slowly. Where is the right of plane zero coming from in a boost converter? Let's consider the direct current. Direct current is something like this. During this phase, the inductor charges. This is T on. This is I diode. During this phase, this T off diode conduct and the inductance discharges on the. What happens if you abruptly increase the duty cycle? Why do you increase the duty cycle? Because you want higher output voltage. So if you increase the duty cycle abruptly, increase the duty cycle means that here your discharge time will start later and your discharge time will be short. So you increase the duty cycle, your inductor current increases a little bit, but your P off time, that is the time where the inductor discharges when the load receives energy, gets energy, is reduced by a large amount. If this is just your output current, you see that the area of the output current, the red output current, is far less than the white output current. So the very moment you increase the duty cycle, you decrease 1 minus D. So you have less time to transfer energy to the output. Then, if you are patient enough, if you wait for some time, this current, the inductor current, will eventually rise, climb up, and eventually you will have something like this, a very narrow, high pulses. But before getting there, you need many cycles because the current to the inductor increases slowly. So you increase the duty cycle, the current to the inductor goes up slowly, and the time that you have to discharge on the capacitor decreases immediately. So the first effect of increasing duty cycle is giving less energy to the output. And if you give less energy to the output voltage goes down. This is the, let's say, hand waving reason why there is a right of plane 0 in the boost converter. Okay, see you Friday.